Hi everybody, welcome back. So next I want to talk about a little bit more detail about what the wave functions are like and how to handle them and use them to get different information that you'll need to know and understand about the orbits of the electrons in the hydrogen atom. So remember that last time I showed you these charts and I explained that the hydrogen atom wave functions look like this. They're functions of the radial wave function R and also of the spherical harmonics, which are the YLMs. And the spherical harmonics are a function of theta and phi. And to get the appropriate wave function, then what you do is you multiply your radial component times your spherical harmonic to get the full wave function for the system. Now to remind you, there's three different quantum numbers, and those quantum numbers are the n, l, and the m sub l, and those correspond to the 3 degrees of freedom that you have for a three-dimensional body like a hydrogen atom. So the first quantum number that I want to discuss should be pretty familiar to you. It's the same basically as the one that we had in the Bohr model, and that's the principal quantum number, also called the energy level, and it's n, okay? And so the n value corresponds to the energy. Bohr got that right. He did that correctly. And the energy would be equal to minus 13.6 eV divided by n squared. So n, the principal quantum number, gives you your energy level. So that one we're familiar with. It's pretty straightforward. The next quantum number is the orbital quantum number, and it's symbolized by a lowercase cursive l. And it's associated with the orbital angular momentum of the electron. It's an integer. And then the third one is the magnetic quantum number, and it's symbolized by m sub l, and it's also associated with the orbital angular momentum. Specifically, it likes to give the z component of the orbital angular momentum. So the values of n can range from 1 to infinity. So there's infinite number of possibilities, starting the ground state n equal to 1 and then going all the way up to infinity. Once you choose your energy level n, though, it restricts the values of the other two quantum numbers. So the values of your orbital quantum number L range from 0 up to n minus 1. And then once L is chosen, the values of m sub L are further selected, and it goes from minus L to L in integer steps. All of these are integers, so they take integer steps. So for example, if n equals to 2, then your possible values of L are 0 or 1. For L equal to 0, the only possible value of ml is 0. But if L is equal to 1, then the possible values of m sub L could be minus 1, 0, or 1. So hopefully that's pretty clear. So here's a handy little table. You can refer back to this table if you like when you're doing your homework or taking your quizzes to understand how this goes. One interesting thing that this table does add is it tells you how many possible values there are. So once you select n, for example, then the values of your orbital quantum number can go from 0 to n minus 1, and so that means that there's n possible values of L. Once you select L, then your orbital quantum number, magnetic quantum number values run from minus L to plus L in integer steps. And so there's going to be 2L plus 1 possible values of a magnetic quantum number once L is selected. Now historically, spectroscopists have used a slightly different notation to indicate what these values are. Instead of using the numbers for L and for N and for M sub L, sometimes they use letters, and this is and then they refer to those letters as shells. So for example, if you are all in the same energy state, have the same principal quantum number, then you're in that shell, and the shells are identified by capital letters starting at K and going up. So if you're in the n equal to 1 state, that's the K shell. If you're in the n equal to 2 state, that's the L shell, and so on and so forth. Now, if you have the same value of n and L, your orbital quantum number, then that is a subshell. Okay, so you're in the same values of the subshell. Now, the subshells are also indicated by letters, but they're lowercase letters, and interestingly enough, they go S, P, D, F. And then once you reach F, you go up in the alphabet. So it would be S, P, D, F, G, H, and so on and so forth. Okay? So the L equal to 0 corresponds to the S state, L equal to 1 to the P, L equal to 2 to the D, L equal to 3 to the F, and so on and so forth. So here's that summarized in table format handy for you that you can refer back to later Doesn't say anything new, pretty much covered all that. Okay, so let's cover some ideas on how to extract information from these wave functions. But first, let me remind you how to find the wave function. So if you know, for example, that you're in the 1s state, that corresponds to n equal to 1 and L equal to 0. So in the tables, you'll be able to find that n equal to 1, L equal to 0 gives you a certain radial wave function R, and then you take that and then you find the appropriate spherical harmonic, okay? So for S, the value is L equal to 0, which means the only possible value is ML equal to 0. And so that corresponds to a specific function, a specific spherical harmonic. And you multiply that spherical harmonic times your radial wave function in the tables to arrive at your full wave function. And then for the 1s state, I've written the wave function out here. 1 over square root of pi a naught cubed times e to the minus r over a naught. Okay, so that's your wave function for your 1s state. Notice a couple of things about this, okay? As your wave function approaches 0, r approaches infinity, and then normalization is present. So the wave function does go to 0 as r goes to infinity, as is required for wave functions. It's also spherically symmetric, so it doesn't matter what value of r you've got, you'll have the same value for your values of r as you swing around in theta and phi. It'll be the same as long as you're the same distance from the nucleus. So it's spherically symmetric. Okay, so remember from last semester that we learned about wave functions, and that if you take the absolute value of your wave function squared, then that gives you your probability density. So the wave function squared for our 1s state is given here, 1 over pi a naught cubed e to the minus 2r over a naught, okay? Now, for this, if you just want to know, for example, about an average or a most probable distance from the nucleus for your 1s state, which might be something that you're interested in knowing, then it's best to just work with the radial component because the spherical harmonic doesn't change things too much for that. If that's the case, then what you're interested really is in the radial probability density function, and they call that P of R, okay? And it's the probability per unit radial length of finding the electron in a spherical shell of radius r with a thickness dr, okay? So that gives that to you. Now, the radial probability density, P of R, is defined as r squared times the little r squared times the absolute value of your radial wave function squared, okay, big R squared. Now, the little r squared comes into play there because remember that if you want a value, a most probable value, that you have to integrate your wave function squared. Well, this is going to be a three-dimensional integral, okay, over all space. And it's got to be in spherical coordinates. So that r squared comes from the volume element for integration for spherical coordinates, r squared sine theta dr d theta d phi. So that's where that r squared comes from, and that's why you have to multiply it times your radial in there, because you need to multiply it when you do your integrations, okay? All right, so here's a plot of the probability, radial probability function P of R. Here it is shown in function form, and here it is plotted out. And so you can see that it starts at 0 at r equal to 0, and then it reaches a peak, and then it tails off, okay? It's not symmetric, okay? It's not symmetric. It's not a Gaussian function. If you folded it in half at the peak, they wouldn't lie on top of each other, and that's because it's got to go to 0 here at the origin, okay? Whereas the other side tails off and goes pretty far out towards infinity. The peak here actually occurs at the Bohr radius. Now the peak on this function, remember that this is a probability density function, so the peak corresponds to the most probable location of your electron, okay? So this peak being at the Bohr radius says that the most probable location is at the Bohr radius, okay? Now, to do this for any given wave function and not just the 1s state, if you want to find your most probable location, what you would do is you would take the derivative of your probability density function and set it equals 0 and then solve for r. So I'm going to prove to you now that the most probable location is at the Bohr radius, a naught. Okay, so if I take my derivative of my probability function dp dr and set that equal to 0, then I get ddr of 4r squared over a naught cubed times e to the minus 2r over a naught. And now this is 2 function of r, so I have to apply my chain rule. So the derivative of the 4r squared over a naught cubed part is 8r over a naught cubed. And then I would add that into the derivative of the second part, with the derivative of the second part. So here I've got my 4r squared over a naught cubed, and then I take my derivative of my e to the minus 2r over a naught. When I take the derivative of my exponential, I get minus 2 over a naught. And then, of course, all of that multiplies times that exponential, e to the minus 2r over a naught. And then I set it equal to 0. Now, because I'm setting it equal to 0 and that exponential appears in both terms, I can cancel it out, okay? So that exponential cancels out, and I just end up with 8r over a naught cubed minus 8r squared over a naught to the 4th equals 0. When I bring that negative part over to the other side, then the negative goes away, and I end up with 8r over a naught cubed equals 8r squared over a naught to the 4th. And then solving for r, I get r equal to a naught. So that proves what I just told you about the most probable location being at the Bohr radius. So, way to go, Bohr. He got something right. Now, you might notice that since the wave function isn't symmetric, you would expect that the average value for r would not be the same as the most probable value of r, okay? And in fact, that's true. The average value of r for the ground state of hydrogen is 3/2 a naught, so it's slightly larger. It's pulled to the right, as that shows. So, according to quantum mechanics, you've got no sharply defined value. Remember that the Bohr model predicted a circular orbit with a very defined specific radius, but that's not what quantum mechanics tells us. It tells us that the probability will be spread out more over a cloud than in a defined circular orbit. So that's going to be slightly different. If you want to find the average value, remember that the way that we did that was we integrated the square of our distribution function times the thing that we wanted to get the average of, and integrated that over all space, okay? So since we want the average position, we would multiply the position r times our probability density, p of r, and then integrate that from 0 to infinity to find our average, okay? If you need a review on distribution functions, the stuff that we covered in Modern 1, you can go back and look in your book on the Schrodinger equation and the Intro to Quantum Mechanics. It should be in there. I believe that's chapter 5. Okay, so our average value of r, these little triangular brackets just indicate an average value, is going to equal to this integral here. Okay, so I'm going to take my probability function from before and multiply by r, and so I get 4r cubed over a naught cubed, e to the minus 2r over a naught integrated from 0 to infinity. And then when I do that, I get this funky little function right here. Now, how did I do that so fast? Well, I used integral tables. Okay, I admit I cheated just a little bit. So from the tables, if you integrate from 0 to infinity, x to the n, e to the minus x over alpha, then the tables tell you that's n factorial times alpha to the n plus 1. Okay, now for us, if we're comparing these two things, that 4 over a naught cubed is a constant that gets pulled out front. The x to the n becomes r cubed, so it's r to the n, and n is equal to 3. So that 3 factorial gives us 6. And then e to the minus 2r over a naught, well, the minus 2 over a naught is goes to our 1 over alpha, okay? And so that's where we get all that. So then, evaluating that integral, I'd have the 4 over a naught cubed, which I pulled out front, times 3 a naught to the 4th over 8 would be the evaluation of that integral. And then when I multiply those two things together, I get 3/2 a naught. Now remember, one of the beauties of online lectures is that at any time, if you find that confusing, you can pause me and rewind and play it again. It's not like class where I'm blurbling on so fast and you can't follow because it's going too fast. You can always slow me down. Okay, so as I hinted in a previous slide, the electron doesn't have defined boundaries. It's in a cloud. a cloud of probability of its location. So that means that basically the charge of the electron, because it's moving really fast, remember last semester we talked about the speeds of the electron being around 2 × 10⁶ meters per second. So it's really whizzing around. And that means that basically your charge is kind of blurred because it's moving so fast, and it's spread in sort of a cloud all around the nucleus. That negative charge is spread all around the nucleus in a cloud. So this little picture here shows the probability density as a function of position in a slice through the atom, with the nucleus being there at the center. Okay, and so the darker blue regions correspond to more probable locations than the lighter region. Okay, well, the next simplest wave function for your hydrogen atom is your 2s state. So that corresponds to n equal to 2 and L equal to 0. Remember, S means L equal to 0. If you look at what your wave function is for that 2s state, it's displayed there. So you have 1 over 4 root 2 pi, 1 over a naught to the 3/2, 2 minus r over a naught times e to the minus r over 2a naught. Okay, this still is a spherically symmetric function that goes to 0 as r goes to infinity. If you plot it out and you show both the 1s and the 2s state on a slice starting at r equal to 0 and going out, then here's your 1s function, and you can see it's got a hump and then a long tail. And then you see your 2s function is a little double hump. So you have a little hump right here and then a bigger hump following it and tailing on out. Okay? Now, the highest value of your probability, radial probability function corresponds to your most probable value. Now, Bohr got the 1s state pretty much right. The most probable value was at the Bohr radius. But remember that we said that r was equal to n squared a naught in the Bohr model of the atom. And you can see clearly here that your 2s state hump doesn't peak at 4 a naught. Okay, so Bohr got that wrong. Okay, it actually peaks a little further away from the nucleus than that. Looks like about 5 or so. Okay, so that's not your most probable location for your n equal to 2 state. So Bohr got that wrong. Okay, some things got right, some things got wrong. We got it all straightened out now. So what do these electron clouds actually look like? Well, if we take not 1D slices, but 2D slices and plot them all out, here they are. This is the n equal to 2 states. So you have n equal to 2, and then there's the s states, or the p states. There's some p states in n equal to 2. And you can see the s states look like spheres, and the p states kind of look like little double humps or figure eights. Okay, so that's our p states. You go up to n equal to 3, and the states get cooler and cooler looking as you go up in values of n. So the n equal to 3 state, it kind of looks like a donut, sort of. And then the 3p state looks like a little figure 8 surrounded by some more halos or something. And then the 3D state looks like 2 kind of figure 8s put together. And you can see they just get more and more interesting looking. Probably this coolest one is the one down here in the corner, the n equal to 15, L equal to 4. That's really cool looking. But you can see the shapes get more and more complex as you get higher up in n. It's actually quite beautiful. If you want to see what they look like in 3D plots, here's the n equal to 2, L equal to 1, and n equal to 3, L equal to 1 states. I think they look sort of like explosions, right? Sort of like blast radii. So this one is sort of a donut blast, and then this one is a mushroom cloud blast, and this one sort of looks like when the Death Star exploded in Star Wars, right? You've got that ring going out and the 2 jets coming out from the side, so they're really cool looking. Now, this isn't just theory, this has been shown. So what you're looking at right now is from a paper published in 2010. And this is scanning telling microscopy images of these electron orbitals. So if you look at the resolution, these little blocks here are just a fraction of a nanometer in size on the side. And you can see that they're showing very clearly what the orbitals look like, and the theory matches the experiment very well. So just to prove to you, if it can't be proved in an experiment, it's not physics, and we've definitely proved that the electron orbitals look the way that they look over time. It's really neat. All right, so what we kind of have our head and we understand what the principal quantum number n is. It's the energy level. We've got meaning there, so we understand that. But let's understand a little bit better about what the orbital quantum number L is, okay? So if you think about what the definition of angular momentum is, it's r cross p, right? And for something moving in a circle, that's going to be mvr, okay? And then the direction of your angular momentum is perpendicular to the plane of your circle given by the right-hand rule. This is all from introductory physics 1150 type stuff. Okay? Now, in the Bohr model, the angular momentum was said to be restricted to multiples of Planck's constant divided by 2 pi, more commonly known as h bar. But Bohr got that kind of right, kind of wrong, okay? It turns out that it's not an integer multiplied by h bar, it's something a little bit more complicated than that. If you do the full-on solution of the Schrodinger equation for the hydrogen atom, according to quantum mechanics, your magnitude or your length of your angular momentum vector will be given by h bar times the square root of L times L plus 1. So it's not multiplied by L, but the square root of L times L plus 1. Okay? Now, think about this for just a second. Your orbital quantum number L can actually equal to 0. Okay? That's an S state. And if L is equal to 0, then that means that the magnitude of your angular momentum is equal to 0. And that causes great difficulty if you're trying to understand the orbits of an electron classically. Because if something moving about an origin, it's got to have an angular momentum if you're thinking about that being a classical particle, okay? So this, in fact, doesn't. So that's a little quirk. Quantum quirk. Notice also that you can have different values of L for a given value of n. So, for example, if you have n equal to 3, then L can equal to 0, 1, or 2. And that's a degeneracy. Remember that we defined last semester a degenerate system as one that have different sets of quantum numbers but the same energy. So this is a degenerate system because the L equals to 0, 1, and 2 for that n equal to 3 state would all have the same energy. Okay? So for the n equal to 2 state, you've got 4 degenerate states. You've got your n equal to 2, L equal to 0, ML equal to 0, and then you have your n equal to 2, L equal to 1, ML equal to 1, 0, minus 1. So that gives you 4 degenerate states for your n equal to 2 system. All right? Okay, so that's all I think we should have time for in this online lecture. Next lecture, I'll pick up there and talk about magnetic quantum numbers and the interpretation of the magnetic quantum numbers. Here's some of my references, and I gave other references as indicated on the images that I borrowed. Thanks for your attention, and I'll see you next time.